Okay. Let me see. I think okay, there's one person missing up this time. Okay, I think we can begin now. Good morning again. Are you all hearing me?
Yes.
Yes, yes. Okay then. Yeah, so to this morning, oh, did I share my screen? It doesn't seem that way. Let me double check here. No, that's not share screen. No. Yeah. Okay, so now I know this morning we are supposed to be moving on to another section of chapter 5. But before I do that, I returned two of your tests to you this morning, and I know one or two persons may have concerns regarding their score. Now we do have opportunities to make up, and so I want to spend some time this morning before we start the lesson with the first makeup that I gave you. That's test 1B. And towards the end of the lesson, I will look at the second quiz number, test number 2. Now, from what I see, more of you did better in that second test than the first one. So it requires a degree of practice. And I know some of us are trying to get the homework done, but sometimes reviewing the tests also helps, because your test doesn't necessarily mimic the homework. So it also requires you to think a little bit beyond. And so that's why we need to make sure when the test is reviewed, you make notes on your test. Because when I give the makeup, basically it's the same test. All I do is change the figures or the letters, but it's the same format. So if you could get to see how the first one was done, or the first version, it should help you when you have to do the second version or the makeup version. I try to have a second version for each, but if everybody does well in the first version, then we don't need to do a second version, okay? And so I will look at the second version of quiz 1, and then we'll do quiz 2 towards the end of the class. Now, when you get a makeup, your second score is going to be averaged with the first. So I can't give you the second score as your final, because you actually did it outside of supervision. And so we want you to, as best as possible, try to aim for as many marks during the first sitting. But when you get that second one, after we'd have gone through the first, the plan is that once you would have gone through that first one thoroughly, it should assist you with doing the makeup, so you could get an even higher score to bring your average to well above what is the pass mark for your course. And remember, for this course, 60% is for the coursework, and your final exam is 40%. So the more points you can get at this stage, is the better it is for you. Okay, so now the first question in this quiz 1B, the answers may vary. And so I'm going to look at the answers that I got from you. And basically, 1B, let me see. With 1B, question number 1. Okay, so I didn't put a tick, I just indicate how many points you got. So if you got full 2 points, that means that your answer was fully acceptable. So I got one answer that said a set of natural numbers equal to or greater than 3 or less than 25. Okay, so that got full points. Now somebody said a set of natural numbers greater than 2 equal to 24. So it's in that case, you got, the person got 1 because we're looking at a set of natural numbers greater than 2, but less than or equal to 24. Okay, so the numbers are greater than 2, but less than or equal to 24. Okay, so that was missing that little section there. Let me see what this other person had there. Okay, the set of natural numbers starting at 3 to 24. That was kind of iffy, but I gave the pass because you start at 3 and you went all the way to 24, and it's the set of natural numbers. Okay, so that got the full 2 points. And then natural numbers 3 through 24. Okay, so those got the 2 points that were fully descriptive of the set. The second one says you are to express each set using the roster method. So number 2, remember now, I think some of you lost a point with that one because you repeated the E. The E should not be repeated. So you get full 2 points if you just have open brackets E, comma, V, comma, N. But if you put E twice, then you lost a point. We just need the members of the set. For question 3 is X is a set of all X, so that X is a natural number and X is greater than 4 and less than or equal to 10. Let me see, I think, okay, one person included 4 in it. No, 4 is not a part of that because it says greater than 4. Other than that, everybody else got it right. 5, 6, 7, 8, 9, 10. So it does not include 4 because it says it's greater than 4. Okay, for question number 4, you're asked to determine if the set is empty. So that's only for 1 point. So that set is not empty. It has a member. So, okay, let me see. No, it's not empty. That's 1 point. Next question, number 5. Fill in the blank with is a member of or is not a member of to make the statement true. So that should be 26 is not a member of. So the symbol should be symbol for is not a member of. Let me see if my thing not right in here. And okay, so that should be it there. It's not a member of. Okay, the next one says find the cardinal number.
Good morning.
Good morning. This is this Miss La Rochelle? Okay. So Miss La Rochelle, we're going through test 1B.
Okay.
Okay. So find the cardinal number for the given set. So the cardinal number for that should be 12 because we have 12. There'll be 12 members of that set. The next one says fill in the blank space with equal or not equal to make the statement true. So 7 says x such that x is a natural number and x is greater than or equal to 5. And then the next set says 8, 9, 10, up to 50. Okay, now in that case, the first set right here, it says x is greater than or equal to 5. So that could go on and on forever. 5, 6, 7, 8, 9, 10, 11, 12, a million, 1,000,001, 1,000,002. Whereas the second set, 8, 9, 10, stops at 50. So the two sets are not equal. So you would put the symbol for not equal for that one. Okay, question 8. Determine if the pair of sets are equivalent, equal, both, or neither. So the first set A is a set of all x such that x is a natural number and x is greater than 12 and less than 17. So greater than 12 and less than 17 would be 13, 14, 15, and 16. Those would be the members of that set. So right away, you could see the sets are not equal because this other set of 13, 15, 17, and 19. But even though they are not equal, they have 4 members each. So 13, 14, 15, 16, that's 4 members. And B have 13, 15, 17, and 19, that's also 4 members. So because they have the same number of members, they are equivalent. Equivalent sets have the same number of members. Okay, equal sets have the same members. Okay, but they don't have the same members, they just have the same number of members. Okay, question 9. Determine whether the set is finite or infinite. In this case, it is finite, number 9. Let me see. I think everybody, oh no, one person put infinite. One person put infinite. Everybody else put finite. But it is finite because it stops. It doesn't go on and on. It stops at, look like that's 1 billion. So it starts at 5, and it seems to be multiples of 5, 5, 10, 15, 20, 25, 30, up to 1 billion. So it is finite. It does have an end. It doesn't go on and on and on. Okay, question 10, it says fill in the blank with, we have 2 symbols there. One says is a subset of or is not a subset of. So for number 10, they're saying the set 2, 3, 7 blank set 1, 3, 5, 7, 9. Now the first set has 2, 3, 7. The second set has 1, 3, 5, 7, 9. So 2 of the members of the first set are in the second set, but not all. So therefore, it is not a subset because it doesn't have the 2. So you would write the symbol, not a subset of. The next one, 65. And then we just have the 65, the number, and then we have the set of all x so that x is an odd natural number. Now 65,
Mr. Allen,
yes,
not a subset is the symbol with the line through it, right?
right.
I put that, but you marked me wrong. I'll send you a message.
Who am I speaking with now? Who's that?
Nairn.
Nairn, let me see. Nairn. Yeah, it's right. I have it right.
Oh, it's the one under that. Oh, sorry. Okay, sorry.
Okay. Okay, now the one number 11 now. 65 is not a subset of that. 65 is an odd number, but because it is not given to you as a set, if they give it to you like this, then you would say it is a member of, but it's not given to you as a set, it's just given to you as a number. So 65, the correct symbol that you could use there is, for this one, would be the symbol for membership. So if they had asked you to say whether it's a member, which is this symbol here, the little E looking symbol, then it would be correct. But they didn't ask you for membership, they're asking you for subset. So the only time one set could be a subset of the other, the 2 of them have to be sets. But 65 by itself is not a set. The only way it would be a set is if you enclosed it in brackets. So because it's not enclosed in brackets, it is not a set. So therefore, it cannot be a subset of this other set, which is the set of odd natural numbers. So that's why in this second one, the answer, it should be, it is not a subset. Okay. The next one, number 12, says determine if subset, proper subset, both or neither can be placed in the blank to form a true statement. So for number 12, 0, 5 is the first set. The second set is 0, 50, and 100. All right. So in this case, that's number 12. Let me see if anybody got that. 12. Okay, one person got that correct. Yeah. Everybody else didn't. I'm not sure if you understood what the question asked, but basically it's saying to you that right away you can see that the first set has 0, 5, the second set has 0, 50, and 100. So therefore it definitely could not be a subset. So that's the giveaway right there. So in order for it to be a subset, they have to, all of the members of the first one must be in the second one. First one only have 0, 5, the next one has 0, 50, and 100. So it's not a subset or a proper subset. So neither of them would apply in this case. Question number 13. Nassau, you was to say whether this is true or false. Nassau is a member of the set New Providence, Bimini, Andros. So in number 13, let me see, everybody got that. Yeah, I see one person put true. One person put true, yeah. But Nassau is not a member of the set containing New Providence, Bimini, Andros. Nassau is in New Providence, but the set does not have the word Nassau in it. It has the word New Providence or the Bimini and Andros. So you're looking for whether or not Nassau is in that second set, which is this not. So that is false. Number 14 is asking you whether 10, 12, 14 is a subset of the set 9, 10, 11, 12, 13, 14, 15, 10, 12, and 14 is in that set. So that is true. Let me see number 14. Did everybody get that? 14, 14. Yeah, everybody got that one. Okay. Number 15, A, B, C is a subset of CABIN. Okay, that is also true. Yeah, A, B, and C can be found in that second set. And then number 16, they're saying to you that the empty set is a proper subset of the empty set. That is false. To be a proper subset, they cannot be equal. Okay, those two sets are equal. Now, if you are given this instead, that with the equal, this would be true, that I just wrote. But this here is false, okay? Because you're saying that it is a proper subset. For it to be a proper subset, they cannot be equal. One set, the first set would have to have less members than the second set, but these two are the same, so it cannot be. Now, if I just say whether the empty set is a subset, which is this statement here, then that is true. But this first one is false. For number 17, you are supposed to list all the subsets of the set W, X, Y, Z. I think most of you got that. Let me see. One person got 2 points because they forgot to put the empty set. The empty set is a part of all the sets. Oh, somebody else didn't list the sets at all. They just told me how many subsets. Okay, the question did say, tell me how many subsets. They said list all the subsets. So you'd list the subset with W, with X, Y, Z, WXY, WXZ, WYZ, WX, WY, WZ, XW, XY, XZ, YZ, W by itself, X by itself, Y by itself, Z by itself. You would also list the empty set, and you would list the, oh, I just see this one here. Somebody had the, you have to also include the set itself, the set which is WXYZ. I see where somebody had it, but they crossed it out. But that should be included as one of the subsets. So you should have 16 subsets in total. Okay. And then the last one says calculate the number of proper subsets for a set with 6 elements. So the number of subsets that you can get from a set is 2 to the n power, which n stands for the number of elements. So that's equal to 2 to the 6 in this case. And 2 to the 6th power is equal to 64. I think somebody got 36. I don't know. You have the correct working and everything, but you just didn't get the right answer. 2 times 2 times 2 times 2 times 2 times 2 gives you 64. In fact, that person, I think I could give you a point for the working. So I could adjust that. If you have the 2 times 2, you have 2 to the 6, and you have 2 times 2 times 2 times 2 times 2. That's multiplied 6 times. So that person, I'll adjust your score and give you 1 additional point for having the working, but your answer 36 is not correct. So that you could get 1 extra point for that. Okay. So, oh, I know why I didn't. Okay, yeah, you still get the 1 point. But this is not the final answer because they ask you for the number of proper subsets. So the number of subsets is equal to 64, but the proper subsets would be the 64 minus 1. Okay, because the set itself is not a proper subset. Proper subsets have to be less than the number of members in the set. So since the set have 6 members, the set the subset which have all 6 members cannot be a proper subset. So the answer should be actually 63. So that's the answer for that one. Okay. Any questions with any of those? Yes, no? If I give you another test like this, you think you will be able to do even better? Yes, no? Or
Yeah.
yes, you think, okay. All right. Okay, so I will look at it, and when I shoot 1C out, if you choose to do it, quiz 1C, you have to do it that same day and get it back to me. I can't tell you when yet. It's going to be either Monday or Tuesday. I'll do a quiz 1C, which will be set up just like this. And I want you to just look at this closely. I gave you the answers, so I hope you wrote your answers down and understand where you went wrong in what you did, so that when you get this other version, you can, do well. Because when it comes time for the final exam, much of what we are doing in these quizzes will be that your final exam will just be a variation of that. And so that's why I'm giving you the extra practice to make sure if you don't understand something and we go through it, I give you another opportunity to work it to improve your understanding, to show that you understand. So when this 1C comes out, I should be seeing even better scores. So I'm asking, if you don't understand something from what we just did, let me know now so I could explain it again. So I hear no response, so I guess we are all good. Okay. Now, the thing is, you have to make sure to read the questions sometimes 2 or 3 times. Don't just go with your first response. Read it carefully before, and as you answer, just think about what you're answering. And if you have to make reference to test 1B and 1A, which we did before, do so. Because the key thing is for you to understand the concept. That's what I want you to do, so that it builds your confidence for later on when you have to. In fact, next week, Saturday, is your first midterm. Now that first midterm, we will have to do that at the BIFS office. So I'm going to arrange with them to facilitate you from 10 o'clock to, I think it's about an hour and a half, 10 to 12. So you're going to have to go in next week to do your first midterm, which is scheduled for next week. The first midterm will contain all that we did from the beginning to today's class. Okay. All right. So since there are no further questions, I will close this, and then we will start today's lesson. And then at the end, I will look at test number 2. Close this. Okay. Go back. Okay, so we're going to lesson number 5. All right, so today we're going to move on to look at okay, we're going to look at chapter 5, 5.4 and 5.5. And so we start slideshow. And so we start on page 264. So on page 264, we're looking at another set of numbers. Last week we looked at rational numbers and order of operations. Today we're looking at irrational numbers. So the set of irrational numbers are those numbers that are neither terminating or repeating. So they do not repeat and they do not terminate. And one that everybody should have heard about is pi. Many of you, when you were in school, you might have used 3.14 or 22/7 as the value for pi, but those are just approximate values. If you look here, you will see this calculated version of pi to, wow, I'm not even sure how many decimal places that is, but it looked like at least 20 places. And if you look at the 20 places or more places that you see here, you'll notice that there is no pattern of repeating. Okay, and you see 3 dots at the end, which means that the value continues on and on. So some numbers like that, what we end up really doing is rounding them off to a certain number of places. Most times, for most calculations, when we just run off to 3.14. But pi is an example of what we call an irrational number. Okay, there's no last digit. It continues on and on and on, and there's no repeating. So if you look at this little clip that came from your book, I think it's page 64, it says in 2002, a Japanese mathematicians at Tokyo University calculated pi to 1.24 trillion decimal places. It took 400 hours of computing time to work that out. And even after going all those number of places, they still did not find any repeating, and it did not terminate. So that's the nature of irrational numbers. They do not terminate, they do not repeat. Okay, so most times when we represent irrational numbers, we have to use symbols to represent them. And so the exact value of pi is just the symbol pi. Any number that we use to represent pi would be an estimate, a rounding off of the value. So one of the concepts we'll be looking at in this section is the idea of square roots, which is something you should be familiar with also. The principal square root of a non-negative number written in the form, as you see, the square root of n is the number which when multiplied by itself gives n. Okay, so we have, for example, looking for the square root of 36. That answer is 6 because when you multiply 6 by itself, you get 36. Okay, now the square root of 36 is called a rational number because the answer is a terminating decimal. You get a whole number as your answer. So therefore, that is a rational number. You can write it as 6/1. 6 is the same as 6/1. Remember, with rational numbers, you could write them in fraction form. Okay, but not all square roots are irrational. Okay, some square roots, maybe I should put here, the book had it not all, but not all square roots are rational. Okay, so this is an example of a rational number because the answer is 6. It's not a non-terminating or non-repeating. The answer is 6. But some square roots are irrational. Okay, so for example, they give you one example here. You ask for the square root of 2. You know, you see this symbol? This symbol means approximately. We cannot find an exact number which multiplies by itself to give 2. And even if you multiply this 1.41214 by itself, you're not going to get 2. You're going to get something very close to 2, but it's not going to be exactly 2. So we cannot find a number which multiplies by itself to give you exactly 2. So something like the square root of 2 is referred to as an irrational. And so you will often see that instead of trying to estimate the value of certain square roots, we'll just leave it in what is called radical form. Okay, so look at the terms here. This here, radical sign, that's this here. So the square root symbol there is referred to as a radical sign. The number under the square root is called the radicand. So that 2 is the radicand. And then the whole thing together is called a radical. So if I ask you to give your answer in radical form, then you would put square root 2. That's the radical form. If I ask you to give your answer as a decimal, then you'd put 1.414214. That's the approximate decimal form of your answer. The radical form is square root 2. Okay? So when we are dealing with irrational numbers, we can either leave it in radical form, or we could give an estimate by writing it as a decimal. So we're going to spend some time looking at this radical form of writing numbers in the next few minutes. All right. Now, another concept you should be familiar with is what we call perfect squares. Okay, a perfect square is a number that is the square of a whole number. So they give you the first set of perfect squares here: 0, 1, 4, 9. What's the next perfect square after that?
10.
No. Look at the pattern. 0 squared, 1 squared, 2 squared, 3 squared. So what should be next?
4 squared.
4 squared. What is 4 squared equal to? What is 4 squared equal to?
16.
16. So the next one would be 16, because 16 is equal to 4 squared. Next should be what?
25.
25, because that's equal to 5 squared. Then we'd have 36, that's equal to 6 squared. Then we'd have 49, that's equal to 7 squared. Then we'd have what? After 49 is what? What's after 49?
64.
64. Okay, 64, because that's equal to 8 squared. All right, so we could continue that forever. So these numbers here, those are all what we call perfect square. So anytime you multiply a number by itself, the result you get is a perfect square. So if you say 10 times 10 is 100, 100 is a perfect square. 11 times 11, 121, that's a perfect square. 12 times 12 is 144, 144 is a perfect square. 13 times 13 is 169, 169 is a perfect square. So anytime you multiply a number by itself, the answer you get, the product, is a perfect square. Now, something to note about perfect squares It says the square root of a perfect square is a whole number. So anytime you get a perfect square, to find the square root, your answer is going to be a whole number. So square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. What's the square root of 144? Square root of 144? Anybody? Square root of 144.
Oh,
12. Okay. Now, perfect squares, we can find their square root. So those numbers would not be considered irrational. All of those are rational numbers. So the square root of a perfect square will give you a rational number. Now, when we have to find the square root of numbers which are not perfect squares, we are going to end up with irrational numbers. And so to work with those numbers, we have what they refer to as some product rules for square roots. And so you'll see here, it says if A and B represents non-negative numbers, then the square root of A times B could be broken up into the square root of A times the square root of B. Or if you have the square root of A times the square root of B, you could combine them to get the square root of AB. All right. So we could either separate the two factors from AB to square root A times square root B, or we could combine the two, square root A times square root B to square root AB. And this only applies when we are multiplying, okay? So you see, product means multiplication. The square root of a product is a product of the square root, okay? So we could use that to simplify finding the square root of numbers which are not perfect squares. So 75 is not a perfect square. You see this example here. 500 is not a perfect square. 17 is not a perfect square. If I gave you a perfect square like square root of 64, you know straight away your answer is 8. That's a rational number. But these numbers here, 75, 500, and 17, they are irrational. They are not perfect squares. So to find their square root, you're either going to have to estimate it using your calculator, or you can leave your answer in radical form. So let's look at how the book worked them out in simple form. And so what they do is to look to see if you can find a perfect square that could divide the number we are looking at. So the first one was 75. Now remember the perfect squares again. 1. Well, we could start with 0 really. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 sevens are 49. 8 eights are 64. 9 nines are 81. 10 tens are 100. Okay, 11 times 11, 121. 12 times 12, 144. So those are just the first set of problems. We could go on and on. I just did a few. So what we're going to do is look for the highest perfect square that could divide, in this case, 75. So as you go down the line, 0, 1, 4, 9, 16, 25. Right away, you should see that 25 there, okay? The next two numbers after that, 3, okay, no, these can't divide. The highest one I could divide, 75, is 25. So we can break it down then. Instead of having square root 75, we could have it as square root 25 times 3. 3 times 25 gives you 75. And then using the rule here, where you say you could separate them into their two factors, then you're going to have square root 25 times 3 is equal to square root of 25 times the square root of 3. Now we know that the square root of 25 is 5. So because 25 is a perfect square. So if the square root of 25 is 5, then we could eliminate that square root 25 and just put 5. Okay, so that's why we have this 5 in front here. Now, the square root of 3. 3 is not a perfect square. We can't simplify it any further. So leaving your answer in radical form, the simplest form for this is 5 square root 3. Okay, let's look at the next one. So we have the square root of 500. If you go down the list of perfect squares, the highest perfect square that could divide 500 is 100. We have another one that could divide it, 25. 25 could divide 500. So we could start with 25, but it's going to end up with a lot of working. So it's best to look for the highest one. So you go down the line to find out, and the highest one is 100. Okay, I guess we could have gone further and looked some more, but just the highest one is actually 100. So what we do then, we split this up as square root of 100 times 5 gives you 500. Then we separate them, square root of 100 times the square root of 5. Square root of 100 is 10. So we could simplify this as 10 square root 5. And so that's the simplest form of that. So we have our answer in radical form. Now, if they wanted you to estimate this, then you would use your calculator and just find what is the square root of 500. But we're not looking to give an estimate of square root of 500. We want to simplify it in radical form. Now, the next one is 17. C was 17, square root 17. But if you look on this list, there is no perfect square that could divide 17. Okay, so it doesn't have any of these numbers that are factors of it. So therefore it cannot be simplified. So the simplest form of square root 17 is just square root 17. And so you can't go any further with that. Any questions with that? Ms. La Rochelle, are you following?
Yes, sir.
Yes, okay. All right, so let us try one then. So we're going to try these three. I'm going to call on you all to work this through. Let me see who else I have here. Okay. All right, so I'm going to start with Miss Nairn. Miss Nairn, are you there?
I'm here.
Okay. So now we're going to start with square root 12. Tell me what we're going to do.
So we're going to look for the highest perfect square that can go into it.
Mm-hmm.
So that would be 4.
4, okay. So square root 12 is equal to square root of 4 times what?
3.
Okay, right. Now, using the rules that they gave us, we could separate this as what?
We can separate this as 3.
What are the two parts under the square root sign? What are the two numbers?
Oh, 4 and 3.
So it's going to be square root 4 times square root 3. Okay, so where do we go from here?
Now we simplify.
Yeah, so there's one of them that you can find the square root of. Which one?
4.
4. So what's the square root of 4?
2.
So 2. And what about square root 3? Can we find a square root for that?
No.
That's an irrational number, so you're going to leave it as 2 square root 3. Okay?
Okay.
So that's the working for that. So if you haven't done it yet, please copy it. And then we're going to go to Miss Pratt for B. So I'm going to write down the perfect squares again. We have 0, 1, 2, 2 is 4, 3, 3 is 9, 4, 4 is 16, 25, 36, 49, 49 and 64, then 81, then 100, and so on. Okay, Miss Pratt.
Hi.
Okay, so we're looking at where am I? Square root 60. So how are you going to break square root 60 down? Square root of 60.
My
Which
microphone,
hmm?
No, I'm listening to you.
Yeah, I'm
uh,
asking you now, which of those numbers can divide 60, the highest one to divide 60? From the list of perfect squares that we have listed here. 0, 1, 4, 9, 16, 25,
Four.
etc. 4. Okay, so if you break that down, that's going to be equal to square root of 4 times what?
15.
15, right? Okay. And then we're going to do what next? Look at the example we have over here.
Okay, so we would do equals square root of 4
Mm-hmm.
times the square root of 15.
Okay, right. Mm-hmm. And then we could find the square root of 4 because we know 4 is a perfect square. Square root of 4 is what?
2.
2. Okay. And then 15 is not a perfect square. So we want to leave it in radical form. So we're going to write it as,
15.
well, not just 15. You have
The
a simple
square root. The
square root.
square root of 15.
Okay. So the answer for that in simplest form is 2 square root 15.
I have a question, Mr. Allen. When I would have done the 2, which is the square root of 4.
Mm-hmm.
And in this case, it has to be either 2, but we know 2 cannot go into 15 without a remainder. So if it could have, that means that we would have still be able to simplify it more.
Okay. Now, you won't be using the 2 to divide the 15 because remember now, this 15 is the square root of 15. So once you find the square root of 4, you're going to put the square root of 4 as 2, and 15 cannot be simplified any further because you cannot find any perfect squares to divide 15. None of these perfect squares could divide 15. So you just leave it as 2 square root 15, and that's it. There's no further simplification for that. Okay. All right, Miss Fernanda, look at C. C is asking you for square root 55. Ananda, are you there?
I'm here.
Okay, so look at the list of perfect squares we have there. Which is the highest one that could divide that?
We only can use these perfect square numbers.
I mean, you could go higher, but if you go higher, that's not going to help you because the number is 55.
No.
So it has to be less than 55 or 55 itself. So if we stop right at 49, because the number can't be more than 55, are any of these numbers from 0 to 49 able to divide 55 without a remainder?
5 and 11.
No, but the 5 and 11 is not on the list.
So, okay.
So your answer is either yes or no. Can you find a
No.
number that can?
No. Yeah.
No.
So
So therefore you can't simplify this any further. So the answer is just square root 55. That's the simplest form.
okay.
So sometimes you are not able to simplify because there's no perfect square that could divide a number without a remainder, or we're giving you a remainder of 0. So therefore, the simplest form is as it is expressed right there. Okay. All right. So they have a study tip on the side. Okay. Which I need you to note. It says there are no addition or subtraction rules for square roots. So this here that you just did, where you can break down the product into the factors, that does not apply for addition. So you see where it says the square root of a plus b is not equal to the square root of a plus the square root of b. Neither does the square root of a minus square root of b is not equal to the square root of a minus square root of b. All right. So do not use these rules for addition and subtraction. They only apply in this case for multiplication. We're going to look at the division later on, but it does not apply to addition and subtraction. Okay. So what we were doing just now was simplifying. Now we also can look at multiplication. And this basically is similar to what we're doing. So here now you're given square root of a times square root of b is equal to square root of a times b. So you're given example 2, where you have 3 situations here. The first one says square root of 2 times square root of 5. So look at the combination of it. Square root of 2 times square root of 5 is equal to square root of 2 times 5 equals the square root of 10. Now 10, there's no perfect square that could divide 10, so you can't simplify it any further. The second one is asking you for the square root of 7 times the square root of 7. Square root of 7 times the square root of 7 is equal to the square root of 7 times 7, which is 49. Okay, and the square root of 49 is 7. This next one, the third one, square root of 6 times the square root of 12 is equal to the square root of 6 times 12, which is equal to the square root of 672. Now, if you go down the perfect square list, you'll find that 36 can divide 72. So you could rewrite this 72 as 36 times 2. And then you could separate now to square root of 36 times square root 2. Square root of 36 is 6. So the simplest form for this one would be 6 square root 2. Okay, so I think these examples are on page 267 of your book, if you have the book. But this is applying the multiplication rules for square roots. So I want you to, using that, what we just looked at, attempt these 3. I'll give you a few minutes, and then I'll call on you to tell me what you did. So go ahead and simplify those things using the multiplication rules.
What page is the square root on?
Page is, I didn't hear you.
What page in the book is it on?
This is, let me see now. Page 267.
Okay.
Okay, Miss La Rochelle, tell me what you did for A.
I did the square root of 3 times 10 equals the square root of 30.
Okay, is there any perfect square that could divide 30?
No.
Okay, so that's it then. Yep, thank you. Okay, Miss Nairn.
Okay, so I did, I simplify it. Square root 10 point, dot 10, and that gives me, square root 100, and
Mhm.
then equals 10.
Okay, thank you. Okay, so that was Miss Nan. Miss Pratt, let's look at the next one.
Okay, so it'd be the square root of 6 times 2
Mm-hmm.
equals 12.
Square root of 12. Mm-hmm.
And then 4 can go into to 12.
Mm-hmm. So that's square root of 4. 4 times what?
4 times 3, sorry.
Okay. So now you could break that up now into
Hold on, I lost now. It's 12 equals the square root of 12. And then we do the 4 times 3 equals 12.
Mhm.
And then we have to find a square, a perfect square that could go into 12.
well, you just did that, which is 4. You said 4 times 3.
Yeah, so sorry, so it'll be equals 4
Square root 4
square root 4, and then we'll put
times
times
you're
3.
gonna square root 3. See, you're gonna separate them into square root 4 times square root 3. And then now you could find the square root of 4 because 4 is a perfect square. So what's the square root of 4?
1 or
No,
4.
no, a number that multiplied by itself to give you 4. What
2, but
number?
2 is gonna
2 is, yeah, 2 is the answer. So it's 2 square root 3.
Oh, I was thinking because 2 was not on the list of the square roots, so I didn't feel that was the answer.
No, you see, the list of the square roots, this perfect square, that's what you use right here where this 4 is. See, once you have the 12, you're going to now look on the list of perfect squares to see if any of them could divide 12. So the one that could divide 12, the highest one was 4. So 4 times 3 gives you 12. So now you have square root of 4 times 3. So you're going to separate it into square root 4 times square root 3. And the square root of 4 is 2. So you simplify that part, but this part here is a radical. There's no, this is not a
Can't go
perfect
any
square.
further.
So your final answer would be 2 square root 3. Okay. So you only look at the list of perfect squares once you have this number by itself here to see if any of them can divide the 12. But after you finish doing that, you don't need to look at that list anymore. You just
Okay.
continue now, finding the square root of the perfect square, and then you simplify the statement. Okay. So unfortunately, because of time, we can't do as much practice as we need to. So that's why I'm asking you to make sure you take notes so that when you do the homework, you have some examples to follow. Your book have examples too, but I know some of you don't have the book. So make sure you take notes so you have examples to follow. So when you do the practice, you see the pattern and it will help to reinforce the concept. Okay. Now, some of you, I see that one of the problems too, sometimes when you do work in class and I can't see what you're doing. So I don't know if some of you, when you put your answer for like B, you see this B, square root 10 times 10 equals square root of 100, your answer should just be 10. It shouldn't have the square root sign. You notice I didn't have a square root sign here because the square root of 100 is 10. So no square root sign needs to be here for this one. Once you find the square root of a number, then you leave out the radical sign. In this first one, we can't find any perfect square to divide 30. So we are leaving the answer in radical form. So you must have your square root sign here to show that we can't break this down any further. Okay. And then in this last one, we could find the square root of 4, which is 2, but we can't find the square root of 3. So we leave that in radical form. So it's 2 square root 3. So just note how the answers are written based on the nature of the question as you do your homework questions. Okay, so we're going to move on then to now look at division, the quotient rule. So in the same way you can combine when you are multiplying, you could do something similar for division. It says if A and B represents non-negative real numbers and B is not equal to 0, then the square root of A over the square root of B is equal to the square root of A over B. So you notice here we have two square root signs in this portion. What they have done is combine the 2 and 1 large square root sign of the fraction A over B. Okay? And conversely, if you started off with square root A over B, which is what they have here, you can separate it into square root A over square root B. So it's sort of similar to what we were doing when we did the rules for multiplication. You start off with A times B, but you could separate it into square root A times square root B. And if you have square root A times square root B, you can combine it into square root of A, B. So with the division, we are doing something sort of similar. You start off with two separate square roots, square root of A over square root B. You could combine it as square root A over B. And if you start off with the combined square root A over B, you can separate it as square root A over square root B. And so we'll look at some examples now. We have this one that says square root 75 over square root 3, and the next one square root 90 over square root 2. So the working for that is shown. So if you have the square root of 75 over square root of 3, you can combine it as 1, square root of 75 over 3. And 75 can be divided by 3. 75 goes in, 3 goes in 75 25 times. Square root of 25. 25 is a perfect square. Square root of 25 is 5. In the second example, we have another similar type, square root 90 over square root 2. You combine it to square root 90 over 2. Divide 90 by 2, you get 45. So that's square root 45. Now, if you look on the perfect squares list, you will see that 9 would be the highest number that could divide 45. So you could rewrite 45 as 9 times 5. So square root 45 would be the same as square root 9 times 45. Sorry, square root 9 times 5. And then you could separate, okay, that's square root 9 times square root 5. The square root of 9, because 9 is a perfect square, is going to give you a whole number as a square root. So square root of 9 is 3. Square root of 5, that's irrational. So you leave it in radical form. So the answer would be 3 square root 5. Okay, so if there are no questions with that, I guess you could try these two. Try those two. Okay, so Ms. Fernanda,
Yeah,
tell me what you
okay.
did. Mhm.
So I divided I made the 80 divided by 5 as 1.
Okay, so that's square root of 80
Mhm.
divided by 5.
And then I got 16.
Square root of 16.
So now the perfect square that can that'll be 4 times 4, would it?
Okay, so what's the answer of square root of 16?
4.
4. So the answer is 4. Okay.
And then I can simplify, so it'll be square root of 2.
Miss Fernanda, why
Right?
are you trying to add more work to the thing?
I wrong? No. So we leave it as is?
Let's start again. You combine the 2 as 1, so you have 80 over 5. Okay. Squared. So when you divide 80 by 5, you get 16. So that's the square root of 16. And then you find the square root of 16. When you find the square root of 16, what you get?
You get the 4.
4. And there's nothing else for you to do. That's it. There's no
Okay.
other symbol there. So your answer is 4.
Okay.
Okay. Okay, so that's Miss Fernanda. Miss Nairn. Tell me what
Okay,
you did there.
so I say 48 over 6.
The square root of 48 over
The
6.
square root of 48 over 6. And then square root 8.
6. Okay, square root of 8. Okay.
And then square root 4 times 2 and equals 2 square root 2.
Okay, you skip one step. Your answer is right, but you skip one step because you
Oh,
went. You're gonna separate the.
Oh yeah, so square root 4 multiplied by square root 2.
And then now the square root of 4 is
2 and then square root 2.
right. Thank you. All right. Now, after practice, you could probably eliminate this step here that I just circled because you could see right away square root of 4 is 2 squared 2, but it's good practice to show it because later on when you're reviewing, you want to know how you got from one point to the next. So that's why it's always good to show your full working at this stage. So when you look back, you can see how you got from one step to the next. Okay, that was Miss Nairn. Okay. Miss Pratt? Pratt, are you there?
I'm here.
Yeah, you follow those two?
Yeah, I follow those two. I still have a, yeah, I follow.
Okay, what about Miss La Rochelle?
I got it.
You got it. Okay, thank you. Okay. Now, even though earlier we said there's the rule doesn't apply to addition and subtraction, it's a degree of addition or subtraction that we can do. Okay. And so it says here that the number that multiplies a square root is called the square root's coefficient. So if you remember in algebra, the number in front of the variable or letter is called the coefficient. Well, the same thing happens with square roots. So for example, it says in 3 square root 5, 3 is the coefficient. And of course, square root 5 would be the radical. Square roots with the same radicand. Remember, the radicand is the number under the square root sign. This, in this case, would be the 5. So it says squares with the same radicand can be added or subtracted by adding or subtracting their coefficients. So in this case, you will see that we have a square root c plus b square root c. The square root, the radicand here is c, the radicand here is c. So because both of them have the same radicand, you can add the coefficients. So a square root c plus b square root c is equal to a plus b square root c. Okay? And the same way we could do subtraction, a square root c minus b square root c is equal to a minus b square root c. Once the radicands are the same, and remember again, the radicand is the number under the square root sign, under the root sign, then you can add or subtract the coefficients. So let's look at some numerical examples. So in the case of a, it says 7 square root 2 plus 5 square root 2. Both of them have square root 2. So they have the same radicand, 2 and 2. So you can add the coefficient, 7 plus 5, which would be 12 square root 2. Now, some persons make the mistake and try to simplify this 12 in radical form. This 12 does not have a square root sign in front of it. So you're not trying to break down the 12. The 12 doesn't have the square root sign. Okay, only the 2 has the square root sign. So you cannot simplify this any further. 7 plus 5 is 12. 12 square root 2 is the answer. In this other example, you have 2 square root 5 minus 6 square root 5. So radicand here is 5. Radicand here is 5. So that means you can add or subtract the coefficient. 2 minus 6. 2 minus 6 is negative 4. So your answer is equal to negative 4 square root 5. Again, this 4, you cannot simplify any further because there's no square root sign asking you to find square root of it. So it's just negative 4 square root 5. Now, this one, you have a combination of addition and subtraction. But the key thing is to look to see if all the radicands are the same. What are the radicands in C?
7.
7. So all have 7 as the radicand. So once they all have the same radicand, we can add and subtract the coefficient. So it's going to be 3 plus 9. And even though this doesn't have a number in front of it, we take it to be 1. So that's why you see they put right square root 7 as 1 square root 7. So it'd be 3 plus 9, 12. 12 minus 1, 11. So the answer then would be 11 square root 7. And so that's how we could combine for adding and subtracting square roots, only if the radicands are the same. And we only add or subtract the coefficients. Okay, so we have 3 here to look at, which pattern what we just did. So I'll give you a couple minutes to do those 3, and then we look at them. Okay, so let's look at those. Okay, Miss La Rochelle, tell me what you did for number 1.
I did, the radical was 3.
Mhm.
So I did 8 square root 3 plus 10 square root 3 equals open bracket 8 plus 10 close bracket square root of 3
Mhm.
equals 18 square root of 3.
Okay, thank you. All right, that was Miss La Rochelle. Miss Fernanda.
Okay, so I have for B, I took 4 minus 9, so it's -5,
Mhm.
and then square root of 13.
Okay, so all right, so I put 4 minus 9 square root 13, so that's equal to -5 square root 13. Okay, Miss Pratt, save the best for you. All right.
Oh, Lord. 7 square root of 10 plus 2 square root of 10 minus square root 10.
Mhm. Mhm.
So open bracket 10 plus 2 close bracket square root of 10 minus square root of 10.
Okay, what is the radicand for these, Miss Pratt?
Hi.
Do that. What's the radicand for them?
10.
That's yes. So all have 10. So that means you could add the coefficients. So what are the coefficients we're looking at?
7 and 2.
We have three of them there. 7 plus 2 minus what?
10.
No. The first one is 7.
Mm-hmm.
Then we have 2. What's in front of this one?
Square 10.
What number is in front right here?
Nothing is in front of that.
Yeah, so what can we put there to keep the value the same?
I don't know.
You don't know? Okay, let me go back here. Let me look. Look, you see this?
Uh-huh.
What does that say?
1 square root of 7.
It says write square root 7 as 1 square root 7. So when you don't see anything in front of it like this, you could write it as 1. You treat it like it's 1. You understand?
Mm-hmm.
Okay, so we go back to this then. And so this here, what we're going to treat this as?
1.
Okay, so that's 7 plus 2 minus 1, close bracket, and then square root 10. Okay. So now 7 plus 2 minus 1 gives you what?
9 minus 1 will be 8.
Okay, so that's 8 square root 10. And that's your answer there. Okay. So this one, anytime you don't see a number, a coefficient in front of the radical, you could treat it as 1. And then you add or subtract as the case may be. Okay. All right, thank you all for that. So we're going to move on then. I hope you've copied these if you made any errors, so you could know what the steps are. And then we're going to move on now to this next stage. Okay, so this says example 5, and that comes from, let me see, page 268 of your book. Okay. It says, in some situations, it's possible to add and subtract square roots that do not contain a common square root by first simplifying. So remember now, with what we were doing, you have to have a common square root before you can add and subtract. Okay? But in this case, in this first example, you don't have a common square root. So you can't add, even though they put the plus sign here, you can't add this because this is saying the radicand here is 8. And sorry, the radicand here for the first one is 2, and the radicand for the second one is 8. But sometimes it's possible to simplify one of them. So in the case of this, you will see where square root 2 plus square root 8 is the same as square root 2 plus 4 times 2, plus square root of 4 times 2. So this portion here, this 8, can be simplified using one of the rules we looked at earlier, because the square root of because 4 can divide 8. 4 is a perfect square. So you could break this 8 down into 4 times 2. So it would be, when you simplify this, they miss a step. They didn't put the, okay, because I would have put this step here, square root 2 plus square root of 4 times square root of 2. So when you find the square root of 4, the square root of 4 is 2. And so that's how they got that 2 in front here. So square root of 4 is 2. And then this is a times, okay, square root 2. So you broke this down to 2 square root 2. And then remember, if there's no number in front of the radical sign, you treat it as a 1. So now that we have simplified the square root 8 to square root 2 square root 2, now the two of them have the same radicand. This is a 2, that have a 2. So now we can add it because 1 plus 2 is 3, 3 times square root 2. So even though we didn't start off with the same radicand, sometimes you can simplify the radical to get it so that they both have the same radicand, and then you can simplify. Okay, oh, they did put the step here, but they put it right here. Okay, split 8 into 2 factors so that one factor is a perfect square. So they have the square root 2 times square root 4 times 2 equals square root 4 times square root 2, which gives you 2 square root 2. So the working for this portion that I just showed is right here. And then now you can add the coefficients. Okay, this next example we'll see on the next slide. So this time, this one is a little longer. They're asking you to add subtract 4 square root 50 minus 6 square root 32. Now, both of these can be simplified. So you notice this is 50, that is 32. You cannot subtract them as they are. But if you broke each down, you end up with 2 as the radicand. So you know 50 would be 25 times 2, and 32 would be 16 times 2. So you could break each down into simpler forms. And so the square root of 25 is 5. So that would be 4 times 5 times square root 2. And then the square root of 16 is 4. So that's going to be 6 times 4 times square root 2. And they have the working on the side here for both of them. So the working for this one is here. And then the working for this one is up here. So they show you how they get the 5 square root 2 and the 4 square root 2. But since this 6 and this 4 was outside, then you're going to multiply 4 times 5 is 20. That's 20 square root 2. 6 times 4 is 24. 24 square root 2. Now the two have the same radicand. So now you can subtract. 20 minus 4 gives you negative 4. Negative 4 square root 2 is the simplest form. Once you convert them, you can now simplify them. Okay. So we have a little study tip here. Sums or differences of squares roots cannot be simplified and that do not contain a common square root cannot be combined in any one term by adding or subtracting coefficients. So you see here, in this case, you have 5 square root 3 plus 3 square root 5. Because they have different radicands, you cannot add or subtract them. The radicands are not the same. This is 3, this is 5. You can only add and subtract if you have the same radicand. Now, in this case, we didn't have the same radicand, but if you simplify each of these, you can get it to a point where they have the same radicand. And once you can do that, then you can simplify by adding the coefficients. Okay? And so that's how you would do something like that. All right, so I want to try these two. Miss Pratt was the last person, so I'm going to start with Miss Nairn. I give you a few minutes to try those two. So Miss Nairn, you'll do the first one, and Miss somebody left. Okay. All right, give you a few minutes to do those two. Miss Nairn and Fernanda. Okay, so let's start, Miss Nairn. Miss Nairn, are you there? Miss Nairn? Okay. Miss La Rochelle? Hold on. No, you hear me? Miss La Rochelle, are you there?
Yes.
Okay. Yeah, I wanted you to tell me what you did with that. With A.
I did for the radical, I 12, I had, okay, square root of 3 plus square root of 4 times 3
Mhm.
was square root of 3 plus square root of 4 times square root of 3. So I simplified square root of 4 times the square root of 3 to square root of 2 times the square root of 3, which
Okay.
gives
All right,
me
hold on. The square root of 4 is what?
2.
So once you find the square root of 2, you don't need the square root sign there anymore. Just put 2,
Uh-huh.
3.
Yeah, okay, I did that.
Mm-hmm.
And
And then now,
then I did 1 plus 2 the square root of 3, which is
Mhm.
the square root of 3.
3 square root 3. Okay. Thank you.
Mr. Allen,
Yes,
I
ma'am?
have a quick question, please, and I don't know if this is a common error, right? But
Mhm.
the square root of 3 plus the square root of 4 times 3. And I'm seeing that I'm incorrect, but I would have put the 1 square root of 3 plus the square root of 3. Why is she using this 2?
Okay, now. Okay, I'm going to call this is line 1, line 2, line 3,
Line 3,
line
yes,
4,
line 3.
4. Mm-hmm. So what you put in line 3?
I have the square root of 3 plus the square root of 3.
Okay. Now, in line 1, we separated we broke the 12 down into 4 times 3. That's 4, okay? And then we separated it right here because we want to get the square root of 4, and the square root of 4 is 2. Then we bring back the square root of 3 because 2 square root 3 would be the simpler form of square root 12. Okay, so you're going to bring back your square root 3. And remember now, because we don't have a number in front here, we're going to treat this as 1. So that's why we have this 1 plus the 2 that is in front here, because now we have the 2 radicands the same. This is 3, and that is also 3 under the square root sign. So we can now add the coefficient. This coefficient here is 1. So 1 plus 2 is 3, 3 square root 3. So that's the steps. Now, I'm not sure you said here, what you have right here, you don't have a 2 here?
No, I put 3 plus the square root of 3.
Where you got the 3 from?
Because it was 4 times 3 that gave me 12.
Okay, so you see this 4 times 3, remember now you're gonna have a square root sign over it because this is still the square root of 12 expressed in another form. So all you've done is broken it down into 4 times 3, square root of 4 times 3. So now you're gonna separate the two factors. So you're gonna have square root 4 times square root 3. Square root 4, the square root of 4 is 2. And the square root of
So we're only doing the square root of 4 because 4 can be simplified?
because 4 is a perfect square. Remember now, only the numbers 0, 1, 3, 2, 4, 9, 16, 25, 36, 49, 60. Those perfect squares, once you identify them there, then you can you could find the square root of them. So once you find the square root of 4, that gives you 2, then you don't need the square root symbol anymore because the square root of 4 is 2. But the square root of 3, we don't have a square root for 3. That's irrational. So you're going to leave it in radical form. So that's how you put this 2 square root 3. This square root 3 also is in radical form, but it's a 1 in front of it. Even though you don't see the 1, it's same as 1 square root 3. So you can now add the 1 square root 3 to the 2 square root 3 because they both have the same radicand. And that gives you 3 square root 3.
Okay. I just have to remember that step 3 that we have to use the square, perfect square.
Yes. So anytime you break down a number, you're looking to find a perfect square that could divide it. So when we look on this list, 4 could divide 12. So you put the perfect square first, which is 4 times 3 to give you 12. Then you separate them into a square root, find the square root of the perfect square, and then you could eliminate that square root sign because you already worked out the square root to be 2. And you put the 2 in front of the radicand, which is square root 3. And now both of them have the same radicand. So now you could add the coefficients to simplify. Okay.
Yeah.
Miss Nairn, are you back?
I'm here.
Okay, so I ask you to do the part B.
Okay, so I lost. So you could walk me through it as I go, please.
Yeah, go
Okay.
ahead. Mhm.
So the first step would be 4. Square root 4 times 2.
Okay, it's a good start.
Minus 7.
Mhm.
Square root, I don't know if this is right. 9 times 2.
Okay, why you think it's not right?
The reason why I was saying it may not be right is because based on what I would have seen, for the first and the second one should have the same. That's right again.
Yeah, but we're finished yet. We're still going through the steps. The main thing you need to do, you see this 18? Look to see which is the highest perfect square that could divide it. And you did say it was 9, right?
Right.
And then for the 8, the highest perfect square that could divide it is the 4. So you're on the right track. But we're not quite finished, so we have to go further now. So you're going to break each of these now. So you're going to say 4.
4 times 2.
Oh, hold on.
Okay.
4 square root 4
Times
square
square
root 2 minus 7 square root 9 times square root 2.
Right.
So, okay. So now you
So
can find this. What's the square root of 4?
2.
So that's going to be 4 times 2 times square root 2 minus 7 times what?
3.
3, because the square root of 9 is 3.
Right.
And square root 2.
Oh, okay. So then 8
Mm-hmm.
square root 2
Mm-hmm.
minus, that's 21, eh?
Mm-hmm.
21 square root 2.
Mm-hmm.
So then that will give me negative 13
Mm-hmm.
square root 2.
Right. Okay. So this one involves a little bit more steps before you can see the common radicand. And so you wouldn't see it right away, but you try to, once you find the highest common, the highest perfect square that could divide each of the numbers, you keep simplifying it to the point where you get a common radicand. Now, it might be that you don't get a common radicand, but once you simplified it, if you don't get a common radicand, you just stop as far as you could go. Because if the radicands are uncommon, if you didn't have 2 and 2 under here, then you couldn't add the coefficients. You would just have to stop as far as you could go with that. But this is the right step for doing B. Okay. All right. So 11. Okay. So now this last part to this is section 5. The section that we're looking at is what they refer to as rationalizing the denominator. Now, to rationalize the denominator means that you are going to write your radical form in such a manner that the denominator does not have a radical symbol. It must just have a whole number. Okay, so in this type of math where we're dealing with radicals, the simplest form of a fraction is one where the denominator does not have the radical sign. Okay, so it says we rationalize the denominator to rewrite the expression so that the denominator no longer contains any radicals. And so we'll look at a few examples here. The first one is 15 over square root 6. So in this case, the denominator is square root 6. But when we rationalize, we don't want square root 6 to be the denominator. So what we do is that we're going to multiply the fraction to get a perfect square as your denominator. So once you multiply both numerator and denominator by the same thing, then you will get it won't change the value of the fraction. So it says that if you multiply the numerator and denominator by square root 6, the denominator becomes square root 6 times square root 6, which is square root of 36, which is equal to 6. All right, so we started off with 15 over square root 6, which is A. And what they did, they just multiply 15 over square root 6 by square root 6 over square root 6. You have to multiply numerator and denominator by the same thing. So once you do that, you're trying to get a perfect square as the radicand for your denominator. So the smallest perfect square you could get is 36. So square root 6 times square root 6 give you square root 36. 15 times square root 6 gives you 15 square root 6. So square root of 36 is 6, and 15 square root 6 could be simplified because you could, this here, what they did, they say 3 into 6 is 2, 3 into 15 is 5. So the simplest form of that is 5 square root 6 over 2. And so that's how that one was simplified. So looking at B, B was square root 3 over square root 5. So even though you don't see a radicand sign here, just remember the rule that we had for division. If you have the squared sign over the whole fraction, is the same as square root 3 over square root 5. So you rewrite it, putting the square root on each. Square root 3 over square root 5. To eliminate this radical sign for square root 5, we're going to multiply by a number so you could get a perfect square. And so what they did, the smallest perfect square you get is 25. So you multiply square root 3 over square root 5 by square root 5 over square root 5. So 3 times that gives you square root 15. Square root 5 times square root 5 gives you square root 25. The square root of 25 is 5. Okay. Now you notice here, we didn't try to cancel anything here because we don't have a number in front of this radical sign. You cannot cancel this 15 because this 15 is not 15 by itself. This is the square root of 15. So the 15 on top here, you cannot cancel it with this 5. If there was a number in front here, then you could do the canceling. Okay, but the number in front there is a 1. Okay, this here is square root 15. So you cannot cancel 5 and square root 15. So your answer in this case is square root 15 over 5. In this last one, it says you have square root 12 over square root 8. Okay, C is 12 over square root 8. So even though you could have used 8 because 8 times 8 is 64, you can find a smaller number in this case because if you multiply 2 times 8, you'll get 16. 16 is a perfect square. So if you use 8, you'll end up with the same answer, but you'll have to do more working. 8 times 8 gives you 64, and then you'd have to multiply square root 8 times square root 8, and then 12 times square root 8. But 2 times 8 gives you 16. So you could multiply both by square root 2. So you'd say square root 12 over square root 8 would be equal to square root 2 over 12 square root 8 times square root 2 over square root 2. And 12 times square root 2 gives you that. Square root 8 times square root 2 gives you square root 16. The square root of 16 is 4. And then because this 12 is in front of the square root sign, you could cancel the 12 and the 4. 4 into 4, 1, and 4 into 12 is 3. So you have 3 square root 2 over 1, which is the same as just 3 square root 2. And so we now rationalize the denominator. The denominator in this case would be 1. But we don't have to put it over 1 if it's 1. And so that's your simple form answer for that one. So let's look at these 3. What can we multiply a by to simplify that? Anybody want to say? 25 over square root 10. What could we multiply by to get a perfect square as our denominator? Anybody?
5.
5 times 10 gives you 50. Is 50 a perfect square? Remember now, we want to get a perfect square as our denominator. So we're looking for 0, 1, what's the number? 1, 2, 2 is 4, 3, 3 is 9, 4, 4 is 16, 16, 5, 5 is 25, 6, 6, 36, 7, 7 is 49, 64, 81, 100, 121, 144, 169, and so on. So we want the denominator to be a perfect square.
25.
25 is, but 25 times, you look, what can you multiply 10 by to get a perfect square under here?
4.
4 times 10 is 40, but we don't have 40 on the list. We're trying to get a number that's on this list. This is 10. We want a perfect square for our denominator. So which number can you multiply this 10 by to get one of these perfect squares?
10.
5.
I didn't hear that.
5.
5? 5
Mhm.
times 10 is 50, but I don't see 50 on the list.
Oh, okay.
I'm
10.
looking 10. 10 times 10 is 100. Is 100 on the list?
It is.
Yeah.
It is, right. So we could use 10. So we're going to multiply square root 10 over square root 10. And then we could simplify. All right. So go ahead now and tell me what's the next step then. If you multiply 25 square root 10, what do you get? 25 times square root 10.
250.
Oh, no.
25 and square root 10.
25 square root 10. You see, this here is square root 10. It's not just 10 by itself. This is a square root 10. It's not, if it was 25 and no square root sign, then you could say 250. But with the square root sign, you can't multiply it. All you could do is simplify it by putting 25 square root 10. And then under that, you're going to have square root 10 times square root 10, which is 25 square root 10. And you could simplify this one to what? Square root, okay, square root of 100. Okay. And square root of 100 is equal to what? What's the square root of 100?
10.
10, right. Now, can you simplify that any further? Can we do any canceling here?
We could cancel the 25.
And using,
5.
okay, so 5 into 25 is 5. And 5 into 10 is
2.
2. So the answer then is 5 square root 10 over 2. Okay, I want you to look at that. See if you have any questions about it. Any questions on that? No? Okay, so let's go on to the next one then. Now, the next one says square root of 2 over 7. The square root should go all the way down. So that could be rewritten as what?
Square root 2 over 7. Square root 2 over square root 7.
Okay, square root 2 over square root 7. Now we're looking to make the denominator into a perfect square. So what can we multiply by?
7.
You can multiply by square root 7. So you're going to say square root 2 times square root 7 over square root 7 times square root 7. Okay, so if you do that, that's going to give you square root 2 times 7 is
14.
okay, you could say square root 14 over square root
49.
49. Okay, that's equal to square root 14 over
Square root of 7.
not square root of 7, square root of 49. What's the square root of 49?
7.
7. So it's just 7. Once you find the square root, you don't need the square root sign anymore. Square root of 49 is 7. So that's just over 7.
Okay.
Now can you simplify that? Can you cancel here?
No, because there isn't a number in the front of 14.
Okay, there's not a number in front of the radical sign. Okay, so this 14 is the square root of 14. It's not 14 on its own. If it was in front of the radical sign, like right here, if you had a 14 here, then you could have canceled the 7 and that 14. What number is in front of this radical sign?
1.
What number? 1. Okay. So if you try to cancel 1 and 7, it will not change anything. So the simplest form of this is square root 14 over 7. Okay. All right. So look at C. C is 5 over square root 18. So remember now, when we rationalize the denominator, we want to get rid of the radical sign in the denominator. So one of the easiest things to do is just multiply the denominator by itself. So you notice here, we had 7, square root 7 times square root 7. For this one, we had 10, square root times square root 10. When we were doing the examples, with this first one, it ended up being square root 6 times square root 6. With B, it ended up being, we started with 5, square root 5 times square root 5. But in some cases, we don't need to use the denominator that's given to you, because look at this one, it was square root 8. We could have used square root 8 times square root 8, but we can find a smaller number that will give us a perfect square. So if you multiply 2 times 8, you get 16. 16 is a perfect square. You could have used 8, but you would have gotten 64, so you'd have to use 8 at the top and the bottom. But you just end up doing more work in, you will get the same result if you simplify it correctly. But if you could find a smaller number that could multiply to give you a perfect square, you could go ahead. Look at 18. Instead of using 18 times 18, is there a smaller number you could multiply by to get a perfect square?
Two?
2? 2 times 18 gives you what?
Oh, no.
9.
2 times 18 gives you what?
36.
36. And is 36 on the list?
Yes.
Yes. So you can use square root 2 then. So you could say that's equal to 5 times square root 2 over square root 18 times square root 2. So that gives you 5 square root 2 over square root of 18 times 2 is what?
36.
36. So then that's 5 square root 2, and square root of 36 is
6.
6.
6. All right. Now, can you simplify that? Can you cancel here?
Yes. No. No.
No. Okay. You can only cancel the coefficient with the denominator. You can't use this 2 because this is square root 2. It's not 2 by itself. So the simplest form for this then would be 5 square root 2 over 6.
Miss Allen,
Question?
can you use 18? And let me see what you get, please.
Yeah. Okay, we could use 18. So if you did that, so we could go 5. So this is, let's do that with 18. 5 over square root 18 times square root 18 over square root 18. So that would be equal to 5 square root 18 over the square root. 18 times 18 gives you what?
324.
Okay, that's 324. That'll be 5 square root 18. And the square root of 324 is 18, so we could stop right there at 18. Now, this 18 that you have under the square root sign could be simplified because 9 can divide 18, and 9 is a perfect square. So you could say equal 5 times 9 times 2 square root of that over 18. So that would be equal to 5 times square root 9 times square root 2 over 18. And the square root of 9 is 3. Okay. So now you could say 5 times 3 times square root 2 over 18. 5 times 3 is 15. That's good. 15 square root 2 over 18. And then this 15 and 18, you could use, what could you use to cancel them? You could use 3. Okay, 3 into 15 is 5. And 3 into 18 is 6. So the answer is 5 square root 2 over 6, which is the same thing we have right here. So you could use the 18, you could use the bigger number. It's just that you'll have to do more working to get it to the lowest form. Whereas if you try to find the smallest number that could multiply to give you a perfect square, you have less working to do. You follow? Yes, no?
Yes.
Yes, okay. So you don't have to use the number that to give you a perfect square. You could always use the denominator itself and multiply the numerator and the denominator by it. But if you don't use the smallest, the one that gives you the smallest perfect square, then you end up with having to do more work and to bring it down to its lowest form. Okay. All right, so moving on then. Let's see. All right, so we basically finished 5.4. And so that was your set of irrational numbers. Irrational numbers. Irrational numbers are non-terminating and non-repeating. So if you try to, you cannot write the exact value for our irrational number because they do not terminate, they do not repeat. And so you'd go on and on and on and on trying to find a value for them if you try to write it down. So oftentimes we use symbols like radical signs to represent them. And if we have to write a decimal value for it, we have to give an estimate to a certain number of decimal places. So in this section now, we are broadening our use or look at numbers to what they refer to as real numbers. So you see the Venn diagram showing you the different types of numbers. Okay. So it says the union of rational and irrational is the set of real numbers. So all the numbers that we have been looking at so far fall under this broad category called real numbers. Okay. So the set that makes up real numbers are called subsets of the real numbers. So we started off with natural, and then natural, we start with 1, 2, 3, 4, 5, 6, 7, 8, and so on. Then we jump to whole. The only difference between natural and whole is that the whole starts with 0. Then we jump to integers. Integers are negative, 0, and natural. So you see, we put integers out right here because integers include whole numbers and natural numbers. It also include negative numbers. Then outside of that, now we have rational, and the rational now would include fractions. Now you see, irrational is not part of any of these because the irrational numbers cannot be represented as a rational number. cannot be written as a fraction because there's no exact value for irrational. But when you combine the rational numbers and the irrational numbers together, they make up what we call a set of real numbers. Now we have numbers which are called imaginary numbers, but that's beyond the scope of this course. We're not going to deal with imaginary numbers. Our focus is on real numbers. Okay, so all the numbers combined that we have looked at so far would consist of the set of real numbers. So we're going to look at this question here, example here. They give you a set of numbers. It says, consider the following set of numbers. List the numbers in the set that are natural, whole, integers, rational, irrational, real. Okay. So the natural numbers would be any number from 1, 2, 3, 4, 5, and so on. Okay. Oh, the answers are here. Okay. Okay. Oh, they would break it down. Okay. All right. So the natural numbers, 7 isn't natural. -7 isn't natural because remember now we're going from 1, 2, 3, 4, 5. This is a fraction, so it's not natural. 0 is not natural. First natural number is 1. 0.6, no. Square root of 5, no. Pi, no. 7.3, no. Square root of 80. What's square root of 81?
9.
9. So even though you see the radical sign here, the answer for this is 9. And since 9 is a natural number, then definitely 9 would be a natural, the square root of 81 would be a natural number. Okay, so the natural number from this list is square root of 81, which is 9. Now they ask for whole numbers. Which number in addition to square root of 81 would be whole?
Hi, Mr. Allen. Excuse me 1
Yes.
second. So how would we write that natural number? You say 9. Would we put that in the brackets? Like how we would do for sets?
No, you just write this, square root 81. List the numbers in the set that are natural. So they just want to list the ones which are natural. So square root of 81 is natural because it is equal to 9, which is a natural number. So the answer for that is just only that number on the list is a natural number. The rest are not. Okay, what
Okay,
about
thank you.
B? Okay, what about B? Which number there is whole? What distinguishes whole numbers from natural numbers? There's one number that distinguishes whole numbers from natural numbers. What number is that?
0.
0. Is there a 0 on that list?
No.
Yeah.
Oh,
there's a
yes,
0.
yes.
So the whole numbers there would be 0, and anything that's a natural number will also be a whole number. So what's the natural number we have there?
-7.
No, negative numbers would be integers.
81.
Oh, yeah.
Square root of 81, right? Okay. Now, integers. Okay. What's the difference between integers and whole numbers?
Negative sign.
Okay, so give me the integers then.
-7.
-7. Mm-hmm.
I see the negative and 3/4 would be thing unknown, right?
Would be what?
I guess that would be an integer.
Well, it's negative, but when we are thinking of integers, we're thinking of whole, we're not thinking
Yeah,
of fractions.
okay.
Mm-hmm.
So
Okay.
that would be it.
Well, all the numbers which are whole and natural are also integers, you know. Because you could be positive or negative. So if you're a whole number and a natural number, you're also an integer.
So that's 0 and square root 81.
Okay, so that would be 0 and square root 81. See, let me go back here. You see here? Natural numbers, that's a small square. It's circled by whole numbers. Then integers circle that. And then rational numbers circle that. So basically what this is saying is that integers, whole numbers, and natural numbers are all rational numbers. Integers would include whole numbers and natural numbers, but not all rational numbers are integers because some rational numbers are not integers. Okay, so you have to look at that Venn diagram to show the relationship. Not all whole numbers are natural numbers, but all natural numbers are whole numbers because natural numbers fall within the circle of whole numbers. Not all integers are whole numbers, but all whole numbers are integers because whole numbers falls within the circle of integers. And likewise, not all rational numbers are integers, but all integers are rational numbers because integers fall within the circle of rational numbers. Then you see a division. There's a division right here where irrational numbers and rational numbers, there's no connection between them. Irrational numbers is a separate group altogether. Okay, so let's go back to what we did here. So we finished with integers. Now we're looking at rational numbers. Now rational numbers would be numbers, any number that could be expressed as a fraction. So which numbers are rational from this list? You could start with what you know already, because you see the circle here. Rational numbers include integers, it include whole numbers, it include natural numbers.
7.
So you could start with your -7,
0.
0,
Square 81.
square root 81.
3 over 4.
Okay, -3 over 4. Anything that could be a fraction or a decimal is
So that'll be 0.6.
okay, that's 0.6 repeat.
Square root 5.
Square root 5. Now that one is you're not gonna get an exact answer for that.
Pi.
You're not gonna get an exact answer for pi either.
7.3.
7.3. 7.3. 7.3. I think that's it, eh? Yeah. Okay, now which numbers there are irrational?
So that'll be squared 5.
Square root of 5.
5.
And whichever one, other one?
And pi.
Pi. Pi. Okay. So the reason those two are irrational is because we do not have an exact value. They do not terminate and they do not repeat. If you try to find the square root of 5, you will see if you put it in your calculator, you're going to get an answer that does not repeat and it doesn't terminate. So your calculator might only be able to go to 5 places or 6 places, but if you had a computer that give you 1,000 places, you still will have numbers running on and on, but they will not repeat. And the same with pi. So those are your irrational numbers. Okay, which one would be real? That's your easiest question. Which one is real? Look at the diagram. Look where you see real. Look there.
Oh, all.
Okay, all of the above. Okay, so all of them would be real. All right. So that's the answers we were looking at just now. Okay, integers, rational, let me see, yeah. Okay, irrational 5 and 5, real numbers. Okay, all right, so that's the answer there. Okay, so the last thing we want to look at, I want to focus on certain parts. I think I want to focus on these here. Let me see, yeah. But, okay, this first one, closure. What does it mean? It sounds commonsensical, but it's something that, you know, needs to be said. Closure property of addition. The sum of any two real numbers is a real number. So if you add any two real numbers, your answer will be real. Okay, so that's a statement of fact. The same thing with multiplication. If you multiply two real numbers, your answer will be real. Okay, so we're not doing any exercises with these two. It's just a statement of fact that you should be aware of. Okay, but these five here, 1, 2, 3, 4, 5, you already have been practicing with, but we're just given a statement to show the properties. Commutative property has to do with changing the order. Okay, so it's something that you are already aware of, but we're just stating the rule concerning those. So what commutative property has to do with is if you change the order in which you add, it doesn't affect things. So if you say 13 plus 7 and somebody else says 7 plus 13, it's the same result. That's what commutative means. It doesn't, changing the order does not affect the sum. Changing the order when adding does not affect the sum. Now, that doesn't apply for subtraction. Because if I say 7 minus 1, the answer is not the same as 1 minus 7. So it doesn't apply for subtraction. But for addition, the order does not matter. The same with multiplication. We have what is called a commutative property of multiplication. Changing the order when multiplying does not affect the result. So 13 times 7 is the same as 7 times 13. But when it comes to division, that doesn't apply because 4 divided by 2 is not the same as 2 divided by 4. So commutative property applies for addition and multiplication. Doesn't apply for subtraction and division. The next property that we want to focus on is what we call associative property. And with associative property, it says changing the grouping when adding does not affect the sum. So if you have 3 numbers to add, for example, if you decide to add the first 2 first, like in this case, 7 plus 2 plus 5, if you add the 7 plus 2 first, or you add the 2 plus 5 first, and then the 7, you'll get the same result. So associative has to do with the grouping, how you group numbers for adding. Associative property is similar. 7 times 2 times 5 is the same as 2 times 5 times 7. Okay, so you could multiply the 7 times 2 first, then the 5, or you could multiply the 2 times 5 first and then multiply by 7. It doesn't affect the answer. So commutative property has to do with changing the order. Associative property has to do with changing the grouping. So with addition and multiplication, it does not affect the answer. But with division and subtraction, your results may change if you change the order or if you change the grouping. Okay, so that's something you should be aware of when you're doing your calculations. And then this last one that we going to focus on is referred to as the distributive property of multiplication over addition. That's something you should be familiar with also, because something we use when you have a number outside the bracket. When you want to remove brackets, you have to multiply both of the numbers within the brackets by the number outside the bracket. So you see here they have A times B plus C. That A must multiply B, and that A must also multiply C. So in the case of this one here, 7 times open bracket 4 plus square root 3 is the same as 7 times 4 plus 7 times square root 3. And so that's the distributive property. And you could see where they're distributing the number outside the bracket to the numbers inside the bracket. So if you had 3 numbers in the bracket, it would distribute all 3. Now they have a couple more properties here, but we're not going to focus too much on those. You could still read them. Identity property of addition, and that means that you can add 0. Zero can be deleted from a sum. All right, so adding a 0 doesn't change the result when you're adding. And in the case of multiplication, the identity property of multiplication, multiplying by 1 doesn't change the answer. So if you multiply by 1, your answer remains the same. So you could always omit multiplication by 1. You could always omit adding 0 because it won't change the result. And then we have the inverse property of addition. I think we looked at that earlier, the inverse of addition. Okay, when you add a number to its inverse, you get 0. When we were starting the number line, we looked at that. Okay, so a plus negative a is 0, and negative a plus a is 0. So the inverse of a would be negative a. So when you add 2 inverses, you get 0. And then the inverse property of multiplication is that when you multiply a number by its multiplicative inverse, so we have what is called additive inverse, and then we have what is called the multiplicative inverse. When you multiply those two, you get 0. Sorry, not 0, you get 1. Okay, so a number multiplied by its multiplicative inverse gives you 1. And a number added to its additive inverse gives you 0. All right, so we have a few questions here asking you to identify the type of property that we're looking at. So it says here, notice that the commutative property changes the order. The associative property changes the grouping. Okay. So in this first one, we have, did we change the order? Or we changed the grouping? Look at A. Did we change the order or the grouping? Anybody with me?
Order.
We changed the order. So we started off with square root 3 times 7, and we changed it to 7 times square root 3. So because we changed the order, then we are looking at what is called the commutative property. Commutative property. Okay? Commutative. And that's the commutative property of multiplication. Okay? So this is a commutative property of multiplication. Okay, now look at this next one. We have 4 plus 7 plus 6 and 4 plus 7 plus 6. So we have the same numbers, no change in order, 4, 7, 6, 4, 7, 6. But what we have done, we have changed the grouping, 4 plus 7 first and 7 plus 6 first. So which property are we looking at? Associative or commutative? Which one has to do with grouping?
Associative property.
Okay, so we're looking now for associative property. And since we are doing addition, we'd say associative property of addition. Okay. Now, this C, we have been given the result after doing certain things. See, we got 2, 2. We multiply 2 times 3 to give 6, and 2 times square root 5 to give you 2 squared 5. So what have we done here? Which one of the properties are we looking at? It's one of these 5 that we're focusing at the bottom here.
Disruptive property of multiplication over addition.
Okay, distributive. Okay, so it's this distributive property. distributive. So we're distributing the 2 to the 3 and to the square root 5. So the distributive property of multiplication over addition. Distributive property. Okay. Now, look at the last one. It says square root 2 plus open brackets, square root 3 plus square root 7. Then square root 2 plus open brackets, square root 7 plus square root 3. Which of those 3 properties do you think we're dealing with there? Miss Nan, what do you think? Is either distributive, commutative, or associative? Which one? Distributive, you're distributing the number outside the bracket to the 2 inside. Commutative, you're changing the order. Associative, you're changing the grouping. So Ms. Nan, what do you think?
Is it commutative?
Okay, and what does commutative mean?
No, associative.
What does associative mean?
Associative means you're changing. No. The order for the brackets.
Okay, what do you see different in those 2? Is the grouping different?
Yes.
Yeah. What 2 numbers are in the first set of brackets?
In D.
Yes.
Oh, that's 3 and 7.
Okay, what about the second set of brackets?
7 and 3. Oh, so they're the same.
Okay, it's the same. Square root 3 plus square root 7, square root 7. So what did they do differently?
They changed the order.
Okay, right. So they changed the order. So because they changed the order, what are we doing? Which property would that for changing order?
That would be. You
Look
can
at
go
the-
back to the slide.
No, it's right at the top. It's one of
Oh.
these two. Mhm.
Oh, that's associative.
What does associative say again?
Oh, sorry. So it changes the grouping. Commutative property
Mhm.
changes the order. Oh, so it's commutative.
Okay, commutative property. Because basically what they did is change the order in the brackets. The first one was square root 3 plus square root 7. The other one was square root 7 plus square root 3. So it's the same numbers. So we didn't change the grouping. If you had changed the grouping, you'd have probably add 2 and 3 first, square root 2 plus square root 3. But we didn't change the grouping in terms of which two numbers we add. We added the same two numbers first. We just changed the order in which we did it. So because of that, we are looking at the commutative property. Commutative. Some people say commutative. Some say commutative. Okay, that's commutative property. Okay. Oh, the answer is okay. All right. All right. So that's basically the content for today. Your homework questions are here. And of course, the answers are there. I don't think I got homework from one person. Let me see. Let me see. Check my email. Nice spreadsheet. Let me see something. Spreadsheet. Miss Nan, maybe I didn't see your email, but did you send the last homework?
Send it this morning.
Oh, you did this morning. Okay then. All right. Okay, so I'll check my email once I finish then. Okay. So the last thing I want to do then is look at, before we go, is the number 2 quiz. Let me see if I could find that. Let's see. Quiz number 2. Okay. That's that. Okay, so okay, so quiz number 2. Let me get my sheet here. Quiz number 2. All right, so the first one, and please stop me if you have any questions and at any point. A intersect B, that should be, oops, what happened here? Quiz number 2. Open it. Adobe. Okay. I want to annotate. And okay. All right. So quiz number 2, A intersect B is what's common to A and B, and the answer for that should be 1, 2, and 4. 1, 2, 4. Close bracket. The next one, A complement intersect B. So that's everything outside of A. So it's usually good to do a step-by-step approach. So everything outside of A would be A complement would be equal to 5, 6, 7, 8. 5, 6, 7, 8. And then B is 1, 2, 3, 4, 5. Let me see, B would be, oops, oh no. Sorry about that, be equal. I don't know why it's doing this. All right, B is equal to 1, 2, 3, 4, 5. Then it's acting up. 1, 2, 3. Sorry, not 1, 2, 3, 4. 1, 2, 3, 4, and 5. And so you're looking for the intersection of those two. And what's common to those two is 5. Okay, I'm going to start over to get rid of these lines here. Stop annotation. Okay. Okay, let me go back. Okay, so the answer for that one should be oh boy, came back. All right. All right, my pen is acting up, so let me see something. Okay. All right, so anyway, I'm gonna have to leave the annotation out because it's acting up. So anyway, this would be 5. For number 3, that should be 6, 7, and 8. Okay, looking for A union B complement. So A is 1, 2, 3, 4. B complement would be everything outside of B. So B is 1, 2, 4, and 5. So outside of B would be 1, 2, 4, 5. That would be 3, 6, 7, 8. So when you find the union of those two, A union that, A complement, sorry, which one are we looking at? 3? Yeah, the answer would be 6, 7, 8. Oh, I just noticed here. Sorry, it's A union B complement. So A union B would be the combination of A and B. So if you look at A union B, that would be 1, 2, 3, 4, and 5. So we want everything outside of A union B. So everything except 1, 2, 3, 4, 5. So it will just be 6, 7, and 8. That's A union B complement, the complement of A union B. So the answer for that should just be 6, 7, 8 within brackets. Okay. So now for question 4, you want you to list the members of A. So that would be 4, 5, and 6. Right here, 4, 5, and 6. 4, 5, 6 is in A. B complement would be everything outside of B. So that would be 2, 3, 7, and 6. Everything outside of B. For A intersect B, that would be just these two here, 4 and 5. That's common to the two of them. And then for 7, A union B complement. Okay. So when you have the A union B, you want everything outside of that. So A union B would be 2, 3, and 7. The complement is outside. Okay, question 8 says that set A contains 25 elements, set B contains 17 elements, and 9 elements are common to sets A and B. How many elements are in A union B? So we had a formula where we add the members of A, the members of B, and subtract the elements that's common. So that would be 25 plus 17 minus 9, which would be 42 minus 9, which gives you 33. Okay, for number 9. Okay. you're asked to find A. Okay, you're given this diagram, this information. Universal set is 1 to 8. A is 1, 2, 3, 4. B is 1, 2, 4, and 5. C is 1 and 5. So you're asked to say what is A union B intersects C. So B intersects C. When you look at B and C, they have the intersection would be 1 and 5. So 1 and 5 is common to B and C. And then you want the union of B and C and A. So A is 1, 2, 3, 4. So 1, 2, 3, 4, and 5 would be the answer for this question. A intersect B, 1 is common to both. So 1 is in A, but there's no 5 in A. So you're going to find the union of those two. So it'll be 1, 2, 3, 4, and 5. Question number 10. You're given a diagram and you're asked to identify the members in these different regions. So A union C, A union C, that's C here, and that's A there. So that would be C, D, E, F, K, P, and R. Between these two, those are the members you have. C, D, E, F, K, P, and R. Question 11 is asking you for A intersect B union C. So A intersect B would be these three, D, C, and F. And they're going to union that with C. So it's D, C, F, and then this here is C. This would be K, P, R. D, C, F, K, P, R. Intersection, yeah, of A and B, and then union with C. And then for 12, you're asked for A intersects C complement. So you want everything outside of the complement of, sorry, everything outside of the intersection of A and C. So A and C is right here, the intersection. So everything except K and F. So you can give all the elements outside of this region right here. So that's A, B, C, D, E, G, H, P, and R. So K and F wouldn't be included, but you would list everything else. Okay, the last page of this asks now for, okay, now so number 13, you have a Venn diagram and you're supposed to label the different parts. I really need this pen to work for that. Let me see if we try it again. Let me go back and try. Let me go back here. Let's see. Next. Oh, this thing's still keeping that old mark. Okay. All right, so let me try my best to show. Okay, so if this was, all right, all depends on how you label it. This is A, this is B, this is C, R. So the first thing you do, you're going to look to see what is common to all three sets. So A, B, and C all have only R is common to all, so that would go in the middle here. Then now you look to see what's common to A and B, except R, because we already put R in. So the only other thing for A and B would be Q. So Q goes here, Q. And then between A and C, aside from R, A and C, A and C have U in common. So U would go here. And then between B and C, aside from R, there's nothing else. So this section here, because it remains empty. Then we look back and see what's in A in total to see what's missing. We have Q, R, and U, but we still have S and T and A. So we'd have to put them here because they're not in any of the intersections. Then we look to B to see what's missing. We already have R and Q, so we just need to put in the P. So P would be here. And then look at set C. We already have U, R. So we need to put in the W and the Y. And then we check now to see the universal set to see if anything is missing. P, Q, R, S, T, U. We don't have V. We have W. We don't have X, and we have Y. So we need to put in the V, and the X to finish off the diagram. So that's how you would complete that one. So you first start off with what's common to all three. Then you look at what's common to two at a time and put in the missing ones. And then you go to each individual set to see if anything is missing from what's given to you. And then once you finish that, you check to see if the universal set, there are any elements in the universal set that's not in the three sets. In this case, it's V and X, and you put them outside the circles. And so that would complete that one. Now the next, how do you get this thing? Stop. Okay. All right. Okay, and this next one, we see. Annotate. No. Let me get the screen right. I want to, okay, right, let's see. Okay, so in this one, it would be itself. All right, so you're given a situation, and it would be similar to what we did with the previous question. Start with the intersection, 22. Let me see. Oh no, color isn't right. Let me double check. Red. Okay. All right, so 22 goes there. And then your total for, let's see. So if you have 22, I think, let me go back here, of those. So you start with what's in the 22 students use all three. So that would be in the center. Now I first need to label these. So I'm gonna use C for, what are the different cars? C. Then we have bikes. I'm gonna put B there. And the other one was public transport. I'll put P. All right, so 22 use all three. So once you do all three, then you need to look at the ones that have two. Okay, so 48 students use car and public transportation. So you already have 22. So you have to subtract that 22 from the 30, from the 48. So you'd have 26 left to put in here. That's cars and public transportation. Then it says 38 use cars and bikes. So cars and bikes is 38. So you already have 22 here. So you'd need to put 16 in this section to get that. Sorry, that should be 16. Okay. And then 26 use public transport and bike. So this right here, 26. So you need to put another 4 here because you already have 22 to make the 26. All right, so we already have the 22 in the middle. We have the different intersection of 2. So now we have to complete the full circles. Let's see. So it says 118 used cars. So you already have 26 plus 22 plus 16. So you need to subtract that from the 118 to find out what goes here. And that should be 54 to make 118. 102 use public transport. So you already have 26, 22, and 4. So you need to subtract these 3 from the 102, which gives you 50. And then 70 use bikes. So you already have 16 and 4 and 22. That's 16 and 4 is 20. That's 20 plus that 42. 42 from 70 gives you 28. So 28 will go right here. And then I think when you add these all up together, you get 256. That's 60, 80, 130, 134, 156, 156, 156, 162, 172, 172, and 28 gives us 200. So we don't have anybody outside that doesn't take any of these forms of transport, so you wouldn't have anything on the outside. So once you fill this in, then you can go ahead and answer the questions. So the first question asks, how many students use only public transportation? So only public transportation would be 50. That would be this set here. So they don't use anything else, only public transportation. The next one, how many students use exactly 2 modes? So it would be this here, they use 2. This here use exactly 2, and this here use exactly 2. So you're gonna add the 4, the 26, and the 16 to get a total of 46. And then how many did not use any of these 3 modes? Well, there's nothing outside of this circle, so it would be 0. Now, if you see me put FT on your paper, it means that your answer is not correct. But because this is what you had in your circle, if you did something wrong in the circle, but you identified the correct region with the wrong answer that you have, you will still get the point. So you wouldn't get the point for the circle, but if you just happen to say put, let's say you had a number outside here. Let's say you had 16 persons who didn't pick. That 16 is wrong, so you wouldn't get any marks for it. But if you answered 16 for D, because that's what you had in your diagram, you'll get a follow-through point. Okay, so sometimes you will see that when I mark FT, means that you did follow through on what you have, but your answer is not correct. It's correct based on what you have on your paper. Okay, last question now has to do with the divisibility. So for that one, you should be able to figure out where you went wrong because it's either yes or no. I think you got all 7 points if you have the correct thing, you minus 1 for each wrong one. So the ones that are not divisible that you should have no for would be 5, 9, and 10. Everything else should be yes. So 5, 9, and 10 should be no. And then the last, let me see if I could just go. Okay, the last question for this one, and I write, is asking you for the prime factorization of 9600. The answer should be 2 to the 6 times 3 times 5. Now I want to demonstrate that because a number of you didn't do it correctly. Let me see if I could open back up the PowerPoint and use one of those slides. This thing is not behaving. Yeah, let's see. Okay. I'm just going to use this space here to show the working for that one. All right, so let me see. Okay, so that's 960. Now you could start it in a number of ways. I started with 10 times 96. When you do the prime factorization, you want to only have prime numbers when you're done. So that would be 2 times 5. 2 is prime, 5 is prime. So you can't break these down any further. Then I use 3 times 32. That's prime. Then I do 2. Also, I use 4 times 8. 4 is not prime, 8 is not prime, so I'm going to continue. That becomes 2 times 2. That's prime. That's prime. Then here I use 2 times 4. This is prime. And then 4, 2 times 2. Prime, prime. So once you end up with all prime numbers, you can stop. So if I write it down in the order I have it, that would be equal to 2 times 5 times 3 times 2 times 2 times 2 times 2 times 2. So I'm going in the order 2, 5, 3, 2, 2, 2, 2, 2. So I end up with 1, 2, 3, 4, 5, 6 2s. So that's 2 to the 6th power times 3 times 5. And that's the answer for that question. Okay, so when you finish, you should only have prime numbers. The prime numbers are 2, 3, 5, 7, 11, 13, 17, and so on. You can only have prime numbers when you're asked to do prime factorization. So you shouldn't have numbers like 4 and 6 and 8 in your answer. You have to break them down to just prime numbers only. Okay. All right, so that is it for today, unless you have a question for me. Next week, Saturday, 10 o'clock at the BIFS for your first midterm. I'll try to do a 1C and get it to you by Monday the latest. I want you to do it and return it so I could mark it and give it to you before the midterm so you could see if you made any progress. I'll send you the sheet with the presentation for today so you could get ahead with your practice for the homework. And that's it for me today. So I trust you have a good week. And Miss La Rochelle.
Yes,
You
sir.
had mentioned something to me about some questions, but I sent back an email for you to specify which questions, but you never got back to me.
I didn't get the email.
Why you not getting my emails? I Yeah. Oh, you don't check your email frequently, Ann?
I do, I just didn't get it.
Okay, but I did respond asking you to say which questions from the homework you said you didn't understand. I just needed the question number so I could know exactly which ones. Okay.
Okay, it was
Okay.
the last one, but I still working on it, so I'll let you know.
Okay. All right. So Miss Nan, Miss LaRochelle, Miss Pratt, Miss Fernanda, that's it for today. And we'll see you next week at the BIFS office for your first midterm. Make sure you have a scientific calculator. You're going to answer all the questions on the paper that's provided, but make sure you have your pen, pencil, no cell phones allowed, just a scientific calculator, and you're good to go. Okay, we'll see you all next week if God's willing.
Okay, good afternoon.
Afternoon.
And, share.